Everyone, hope you guys are doing great. This is going to be a lecture about solving Unit 4 past paper questions regarding all the topics which we mentioned in Unit 4, either the ones that we mentioned in class, the ones that we mentioned in the videos. The file I'm going to be using to solve these questions will be sent to you guys on the application afterwards, and you can always recheck on this video to practice after studying the unit from the videos or from your book or notebook, or depends on how you go for it. It's always good to have a place where you can solve problems. I'm gonna go over these ideas. Some of them you might have seen in the previous videos, or we might have solved in class. But if it's a repeated idea or something, I'll go over it real quickly. If it's not, I'll solve it, It's just to give you an overview on what you need to expect to be asked about when it comes to this unit. I'm not going to take long talking about the introduction. We're going to go straight to it because I'm going to try to solve as many questions as I possibly can. If a question seems unclear or you don't understand what I've done here, try to repeat watching the video and seeing the steps again. And if it still seems unclear, we can speak about it. Send me a message and I'll respond to you with the right way of solving it, okay? Starting off with the first question here, it says the diagram shows a ball of dough with the mass of, this is the mass right here, okay, 580 grams, and the height of 92 centimeters above the floor. I want you to remember that these questions are not only to do with the last lesson we took, no, it's with the entirety of Unit 4. Okay. Hold on, let me lock the zoom in, zoom out. Calculate the increase in gravitational potential energy stored in the ball of dough when it's above the floor. You can, it's very simple here. You have a ball, the mass of it is 580 grams. The height of it is 92 centimeters, and it wants you to calculate the gravitational potential energy. Okay, wants you to calculate the GPE. From what we studied in this unit, we all know that the gravitational potential energy, GPE, equals mass multiplied by height multiplied by gravity. And note, always gravity is assumed to be 10 newtons per kilogram. Okay. We're gonna go on into solving this, but we're gonna face two little issues, but at this stage there shouldn't be issues for you guys. We noticed that the mass was given to us as 580 grams. We need to switch that to kilograms. Okay, and we also noticed that the height was given us to as 92 centimeters, and we gotta switch that to meters instead. We know from switching from grams to kilograms we have to divide by 1,000. And we know from switching from centimeters to meters, we have to divide by 100. This ends up being 0.58 kilograms and 0.92 meters. All right, and we just gotta put them all in the calculator and multiply the numbers. So the final answer to this would be GPE equals the mass, which is 0.58, multiplied by the height, which we changed to become 0.92, multiplied by gravity, which I also told you that is always 10 on Earth, and this will be given to you in the very first page, but with repetitive questions you'll know it without even checking the very first page or whatever. You're gonna multiply those three numbers together, and the amount of energy the ball of dough has after multiplying those numbers together happens to be 5.336 joules. Okay, because joules is the unit for energy, don't forget about that. It's already written here, so you just gotta write the number, which is 5.336. All right, I recommend you revise your formulas, you revise all the topic before you enter such video, but yeah, like you should know this formula, and it's just normal conversion of these units. This one you switch it up to kilograms, this one you switch it up to meters, and yeah, you just gotta use the formula afterwards. Okay, the ball of dough hits the floor and does not rebound, which means the moment that it hits the floor it gets stuck there. Describe the energy transfers taking place when the dough is dropped. After it has hit the floor, you should refer to the energy stores as well as transferred between energy stores in these stages. Before the dough was dropped, just before the dough hits the floor, after the dough has hit the floor. So you just need to describe all the energy stores, if they're empty, if they're full, and whatever. And we're starting off from the first point, which is before. Okay, and before the dough was dropped, okay, checking by the diagram up here, you can see that it's held at a high point. It's not moving, so it doesn't have kinetic energy before it's dropped. Okay, but there is height and there is gravity trying to pull it down, so it does have gravitational potential energy. And those are the two stores that you can consider now. I can't think of anything else. So all the energy right now is stored in the gravitational potential energy store. There is no kinetic energy. All right, so that's the section of before the ball being dropped. All you need to answer it with in this case is saying that before the dough was dropped, all energy was stored in the gravitational, or for short, GPE store. Okay, now we need to go to the second point, which is just before the dough hits the floor. All right, before the dough hits the floor, it means it has moved from the position which it's in up there all the way to the position which is down here, but it hasn't hit the floor yet. Okay, I'm sorry for the bad drawing. Just trying to draw the ball up here, down here again. Okay, it hasn't, just before it touches the ground. Usually when objects fall down, the moment they reach the very, very last point of them is when they reach their maximum speed. Okay. All right, now because it was dropped down and it just reached the maximum speed, and the question emphasizes on just before it hits the ground, you can assume that the gravitational potential energy becomes zero because there is no height. You're literally pretty much almost touching the ground. Your height is zero. Therefore, your gravitational potential energy is zero. But what also happens here, when you drop something and it starts falling down, at first it's not moving, and then suddenly it's a bit faster, suddenly it's faster, suddenly it reaches the fastest point when it's about to hit the ground. Okay, so the kinetic energy right here is at its highest point. So what happened in this scenario, to clarify everything that I just explained right here, is when it's about to hit the floor, all the energy that was before in the gravitational potential store has turned from there into kinetic energy. Okay, now we gotta go down there and just clarify the second point, which is just before the dough hits the floor. Okay, all energy is transferred from the kinetic store, oh sorry, my bad, all energy is transferred from the gravitational potential store to sorry again, to the kinetic store. All right, now the thing is we still have one more section, which is after the dough hits the floor. I'm gonna write it right here since we have a lot of space. After the dough hits the floor, the question tells you that the moment it hits the floor, it does not rebound. So the kinetic, like it hits the floor and it stops moving. The kinetic energy becomes zero. Okay, where did all the energy go to? Well, you need to imagine the scenario in your head. If you drop dough on the floor, you will hear a loud smack. So a lot of this energy has turned into sound energy. And everything, if you smack anything or something hits something, automatically some heat releases. So after the dough hits floor, it's the floor, all energy from the kinetic store, because that's what it was before, is transferred. Let's write them down again. Is transferred into sound and heat energy. And this is a full explanation of the scenario. At first, It's not moving, so no kinetic energy, and the only thing that you have is gravitational potential energy because there is height and gravity is trying to pull it down. After that, the ball drops all the way and it reaches just before it's about to hit the floor, like right here. The height is almost zero. Therefore, the gravitational potential energy now doesn't exist because there is no height, but what exists is kinetic energy because it's like the moment it's about to hit the floor, it was moving at a very high speed. Okay, so all the energy switched from gravitational potential to kinetic. After it hits the floor, which is the last stage, it's no longer moving, so kinetic energy is not the case anymore, but it changes to sound and heat. Okay, and that's what I wrote in the lines down there. All right, let's move on. We took a lot of time in this question. Next one. A teacher makes a hot drink. He puts the drink in a cup designed to keep the drink hot. The photograph, and cross-section diagram both show the cup. So it's a cup, those cups that when you pour something hot in them, it stays hot and it doesn't cool down. You can see right here that the teacher was trying to keep their drink hot. What does it have? It has a plastic lid. It has a shiny metal on the outside. It has a vacuum, some air in the middle, and it has a shiny metal on the inner surface. What it asks you in this question is to explain how the design of the cup keeps the drink hot. Refer to methods of energy transfer in your answer. This is a question to do with the first chapter. Look, it's 6 marks. With the second chapter, okay? Which is, remember, the entire point of the cup is to keep the drink hot. So you need to think about ways to transfer heat. Okay? We studied, if you remember with me in class, 3 ways that you can transfer heat. Way number 1, we called it conduction. Okay. Way number 2, we called it convection. Way number 3, we called it radiation. 3 ways in which that heat transfers, all right? And you're trying to say, why is this design of the cup very good at countering these? Because remember, you have heat energy inside, and your only concern is that the heat stays inside, it doesn't go outside. You don't want it to go outside. Okay, so you're trying to think about, why is this cup good at it? All right, remember with me that we also studied another thing in chapter 2. We studied something to do with radiation, if you remember with me. We said radiation has something to do with shiny, okay, and dark objects. We said dark objects absorb it quickly, shiny objects don't absorb it, but also the point I'm trying to say, remember that shiny objects don't give it away, they hold on to it. Okay, they hold heat energy. And this is very important to answer this question. While dark objects, they give it away easily. Okay, so we can use these points all to pitch up some answers, but in order to kind of not waste a lot of time with this question, I have looked up the mark scheme for it and I attached it below it. We'll notice that all of them have to do with the stuff I mentioned right here. So look right here at the very bottom. It's worth 6 marks, by the way. You need to mention 6 points of how the cup keeps heat energy inside and doesn't let it escape. Ones that I can tell you easily is that, first of all, the lead is made out of plastic. Plastic is not a good heat conductor, so it doesn't let the heat escape because it doesn't conduct it well. Here you have a vacuum in the middle, which means it's some air. And air, when it's between 2 solids, it makes it very difficult for heat to transfer. Okay, another thing is that you have a shiny metal on the inside and a shiny metal on the outside. And shiny objects, they don't give away heat energy, so it stays wherever it is stuck. Okay, and those are just 4 points that I thought about off the top of my head based off the stuff that he mentioned right here. All right, we can check the rest of them down there. It says right here, any 6 from, so it gives you 1, 2, 3, 4, 5, 6, 7, 8, 9 options to answer it. And as long as you mention 6 points, and there are 6 of those 9, you would get the good answer for it. All right, so we can check that it says the cup slows down, stops energy transfer to the surrounding, which is a startup point, and they would have given you a mark for it, even though you wouldn't have explained how, but you know. Even if you said use the words energy is trapped, you would have still like allowed. Okay, relating to conduction, now look, you can answer it with conduction, convection, and radiation, and you need them in order to answer such a question. Okay, you can look at the first one right here. It says that vacuum contains no particles, therefore conduction doesn't happen. And he's talking about what? He's talking about this small section right here. This in the middle right here, the vacuum that you can see that it's highlighted on this side, this one. Because remember, it's solid, and in between he leaves a thin layer of vacuum, okay? So that one interrupts conduction, which means the energy can't escape using conduction. Second point, it says that it reduces conduction through the sides. Okay, plastic lead is a poor conductor. That's one of the ones that I thought about. Convection, air is trapped by the lid. That's fair enough, because remember with me, it's you pour coffee inside of there. Probably some smoke is gonna try to escape, but you block it with the lid on the top. You stop convection from the surface because you're using a lid. Again, both of them are like, they give the same meaning. Okay. Related to radiation, the shiny surfaces, look, are mentioned twice. There are 2 points of which that we needed to talk about. And also it says energy transferred by radiation is reduced stop, which is a startup point. So you don't need literally to have them numbered as 1, 2, 3, 4, 5, 6, if that makes sense. But that's better for you to guarantee getting a good mark on a question. But again, you just need to think about the 3 methods of transferring heat energy and just say how does the cup counter them, okay? It gives you many options of you to write them, saying that, okay, allow that it stops evaporation, which is the smoke going out. Allow that the inner surface reflects heat because it's shiny. You can basically have like at least out of these and the allowed parts, you have at least 10 ways of answering the question, okay? Moving on to the next one, it shows you a diagram of a truck traveling along a horizontal road. The driver sees an obstacle in the road and then applies the brake. Oh, this is a throwback. Which factors affect the thinking distance? This is like unit 1 stuff, okay? Which of those affect thinking distance? And the right answer, because we're talking about the driver, again, thinking distance, think about the driver. So what would affect the driver? Do the conditions of the tire affect the driver? No. Does the consumption of alcohol affect the driver? Last time I checked it does, but let's check the other options. Does the mass of the vehicle affect him? Nah. The condition of the world? Nah. Whenever it talks about thinking, you need to remember that the driver, the human being, is the one doing the thinking. So, this is the right answer. Okay, so, alright. Okay. Which of these factors affect both thinking and braking? Alright, so remember, not just thinking, not just braking, you need to think about them. The conditions of the brakes, they affect the braking distance. Do they affect the thinking distance? Nah. The conditions of the road? Nah. Mass of the vehicle? Nah. The only thing that affects both the thinking and the braking distance is the speed of the car. Because even if the guy was Michael Schumacher and he had the most amazing reactions in the universe, if his car was moving fast, the distance he would travel would be fast, even if he like kind of hits the brakes almost instantly. But you can just remember that the speed is the only thing that affects both of them. Alright? Now, the reason I put this right here is because it has a section that has to do with our unit. Look here, the truck experiences a braking force of 46,000 newtons. Alright, state the formula linking work, force, distance. And we studied work in this chapter. The formula is work equals force multiplied by distance. Good. The truck has this number of joules of energy in its kinetic energy store before the driver applies the brake. The braking force does work on the truck to reduce the kinetic energy of the truck to 0 joules. The braking distance is defined as the distance required for the kinetic energy store to the truck to reduce to 0 joules when the brakes are applied. Calculate the braking distance of the truck. And nothing complicated here at all. You already know the force, okay? And you already know the energy of kinetic, which I told you is just calling it kinetic energy to distract you, but energy and works are in such scenarios the same thing. So you can just put 590,000 joules instead of work equals the force which he gave you as 46,000 multiplied by the distance which I'm trying to find. Alright, I'm trying to calculate distance. What do? I take this to the other side as a division. Okay, it becomes, just to reorganize it to make it look nice, distance equals energy, or in this scenario work, divided by the force. And you just need to divide both of them. Give me a second to do the calculation. You need 12.83 meters. Are we good? Should be good. The only thing that's kind of distracting here is that you need to understand that because the car is moving forward, there is no gravitational potential energy whatsoever. Therefore, kinetic energy is the same as work in this scenario. Okay, because it's the only energy of movement that you have. And work is energies of movement in general, including kinetic, gravitational, and elastic together. But in this case, you only have kinetic energy, so it's the same as the work. You can just go to your formula, replace this number with work. You have the force up there, and your missing thing is the distance. You can calculate it with no issues. The brake increases in temperature when the truck is braking. State the name of the energy store that has increased for the brakes. In this scenario, I mean, he already answered it. Because the temperature is increasing, okay, the energy store that increases is the thermal energy store. Just an easy one, Mark. State the method of energy transfer to the truck. State the method of energy transfer from the truck to the brakes. In this scenario, the method of energy transfer, mechanical work, or in other ways we can say friction. Okay, but when we took the lesson of ways of energy to transfer, I'm not talking about heat energy transfer, I'm talking about normal energy transfer. We mentioned that there are 4 methods: heat by particles, heat by radiation, if you remember with me, that's how heat transfers. And then we said there is mechanical work and electrical work. Anything to do with forces, stopping, movement, stuff like that, it's all to do with mechanical work. But I'll just tell you, because it's the way that brakes operate, if any of you wrote friction, it would have like counted correctly. Okay, but the method of transfer energy, in this case, it's mechanical work. Moving on to the next question. They should start getting easier because they will start repeating points at this, repeating ideas at this point. A student uses the, whatever that word is, to investigate the force needed to pull a block along a ramp. All right, this is the ramp and it's tilted right there, and you have the distance, and you have the force he's pushing with it, and you have the height of it right here in case you need it in another part. State the formula linking work done, distance moved, and the direction of the force. Work equals force multiplied by distance moved in the direction of the force. The student pulls the block 0.98. You can see that from the diagram with the force of this. Show that the work done on the block is 23 newtons. Calculate, and it should be about 23. We all understand that work equals force multiplied by distance. We calculate work by taking the force, which is 26, multiplied by the distance moved, which is 0.89. Second to do that in the calculator, please. And the right answer is 23.14. And what's the unit for work? Joules. Right. Moving on to the next one. The block has the mass of 1.3 kilograms and moves vertically upwards 0.11 meters. Interesting. Calculate the increase in the gravitational potential energy store. The formula for gravitational potential energy, let's switch up the color because I got bored with black. GPE equals mass times gravity times height. Gravity is always 10. The mass is 1.3. The height is 0.11. So GPE equals the mass, which is 1.3, multiplied by gravity, multiplied by height, which is 0.11. And you just gotta multiply the 3 of them. And if you put that on the calculator, it would give you the answer of 14.3. No issue. Explain why the work done to move the block along the ramp is greater than the increase in the gravitational potential energy store of the block. We already discussed this point before. Now look, work is a combination of all movement energies. And if you look at this block, it didn't just go up, because that's what gravitational potential energy is. It's a movement of up and down. No, it went up, but it also moved to the left. Okay, so work in this scenario is both. I just want to explain a small point. Work in this scenario is the gravitational potential energy plus the kinetic energy. The energy that moved the block left and right plus the energy that moved the block up and down. or sorry, in this case, it just went up and it just went left. All right. So when we calculated the gravitational potential energy right here, we just calculated how much energy was used to lift the block upwards. But we didn't calculate the other section, which is how much energy was used to move the block to the left. All right. That's the idea behind here on why the work done on the block is greater than the increase in gravitational potential energy store. Okay, you just need to write something that explains that the work, sorry, I don't know why I wrote the line. You just need to write something that explains that the work is both gravitational potential energy and kinetic energy. So the reason it's greater than it, it's because we're missing the kinetic energy. The student suggests it's better to use less steep ramp to raise the block though through the same vertical height. Okay. Discuss the advantages and disadvantages of using a less steep ramp. All right, and I want you to understand two things. If you use something that's less steep, okay, this would affect how much kinetic energy you need, and it also would affect how much gravitational potential energy you need. And you need to explain it in this question by answering how does it affect this one and how does it affect this one. All right, meaning in such scenario, this one wouldn't be affected because it's the same height you're traveling, but the kinetic energy can be affected and the work done can be affected. All right, I'll make it very simpler here and answer what would be an advantage and what would be a disadvantage of using a less steep ramp. A less steep ramp, by the way, it doesn't go higher as much. It's like this one. So we'll start with the advantages. First of all, in order for you to push it, the advantage number one is that you need less force. All right. Force needed to move the block. Okay, and that's the first advantage. Okay, the green ones are going to be advantages. The second advantage you could also think about is that it's going to be easier to push, or I don't know, pull, for you to make it up there, making it like take less effort, you know. Now those are the advantages of you taking a long ramp. The disadvantages are pretty obvious. Disadvantage number one is it's gonna take longer time. Okay, and the disadvantage number two is that you will lose a lot of energy as thermal energy. Why? Because if you use a steeper ramp, if you use a less steep ramp, it's gonna be longer. You're gonna be pushing the box a longer distance. You're gonna face a lot of more friction because you're I don't know, like the box is scratching with the ground more, and all of that is gonna release more heat energy to the surrounding, making you require more work. Okay. But at the end of the day, in this case, it makes it require more work, but you're using less force, all right? So it kind of balances itself out. You don't need to look at the work part about it, because some people would argue that if you use a high, the same one that's displayed, that one is very steep, making you need to push it up with a lot of force. But if you use the other one, it's not as steep, so you don't need a lot of force. Yes, the distance is longer, but you just gotta focus on what's a good thing about it and what's a bad thing about it. Because, you know, some people prefer that way of pushing it up, some people prefer the other way of pushing it up. This is a satellite launched to orbit around the Earth. The rocket carrying burns fuel to accelerate upwards. As the rocket burns fuel, the energy in its chemical store reduces, and the energy in its kinetic store and gravitational store changes. State how the kinetic store of the rocket changes when the rocket burns fuel. Obviously, the more it burns fuel, the faster it's gonna move, so it increases. Okay. State how the gravitational potential store energy of the rock changes as the rocket burns fuel. Also, it gets higher and the height increases, so it also increases. No issue with both of them. Remember, the rocket is going faster and it's going up. So this one increases because it's going up. This one increases because it's going faster. Okay. Oh, there's something else I checked right now and I forgot. I just remembered right now quickly. Sorry about this question right here. Let me fix it. 1.3 times 10 times 0.11 doesn't give you 14.3. It gives you 1.43. So I'm very sorry. All right. The rocket engine stops burning fuel. The rocket continues to go further away from surface of the Earth. The table gives you some statements about the rocket's energy stores. Add a tick to the table to show which two statements are correct. So two of them are going to be correct. It's talking about once it stops burning fuel, the rocket continues to go further away. So the rocket is going up, okay, and it's no longer burning fuel, okay. Okay. Basically, we need to take a look at all statements mentioned right here. First of all, the rocket is going up still. It's still going away from the surface of the Earth. Keep an eye on that. But the engine stops burning fuel. All right, and those are the two key points we need to use to answer here. The rocket not burning fuel anymore, meaning its speed is no longer increasing. No, it's still going up, but kind of like it was going up very fast, and then suddenly it's going up, but slowly, if that makes sense, because it's no longer burning fuel. Okay, so the kinetic energy has to decrease because the speed went down. And the other thing, since it's still going up, even though it's going up slowly, the gravitational potential energy continues to increase. Okay, I hope it's clear. So let's look for the options right here. Gravitational store increases, yes. The gravitational store stays the same, no, because it says right here it goes further away from the surface of Earth, which means it's still going upwards, so no, it doesn't stay the same. Gravitational store decreases, impossible. Kinetic store increases, no, because it's not burning fuel anymore, so it's not getting faster. It's quite the opposite. Stays the same, no, because, you know, it stopped burning fuel, so it has to start slowing down. So the right answer is the kinetic store decreases, okay? The photograph, how long is the recording? 31 minutes, all right. The photograph shows a toy car. When the toy car is pulled backwards, the energy stored in the elastic store as the rubber band is twisted, Okay. When the car is released, some of the energy from the elastic store is transferred to the kinetic store of the car. The remaining energy is transferred into the thermal store and the surrounding state. What is meant by the principle of conservation of energy? And you need to define the principle of conservation of energy, which says energy cannot be created or destroyed, but transferred from one store to another. Right? You just need to write what I said. The car is pulled backwards so that there is 165 joules of energy in its elastic store. When the car is released, this energy is transferred to the car's kinetic energy store with an efficiency of 15%. State the formula linking efficiency, useful energy output, and total energy output. And we know that efficiency equals useful energy output divided by total energy output multiplied by 100%. Okay. Calculate the energy transferred into the thermal store and the surrounding, and look at the fact that it has 4 marks because it's a very, very, very nice question. You know that right here from what it says, the car is pulled backwards so that there is 165 joules of energy in its elastic store. This is the total energy output. And you know that the efficiency itself is 15%. All right, and you know that the useful energy right here is unknown, but focus here that in the question it doesn't ask you to calculate the useful energy. No, it wants you to calculate the energy transferred into the thermal store and the of the surrounding, which is it's asking you to calculate the wasted energy. There are 2 ways for you to go about answering this question. I like it a lot, by the way, personally. The first way is you can calculate the useful. Okay, and since you know the total being 165, you can just do 165 minus whatever you calculated as the useful energy to give you the final answer. The other way I'm going to use is changing the percentage from 15% to 85%. What I'm going to do right now is I'm going to solve it with both ways. Way number 1 is I'm going to calculate that useful energy output. I know that efficiency equals useful divided by total multiplied by 100%. Okay, let me try to calculate the useful up there. All right, let's put everything in its position in the right numbers. The efficiency in this case is 15%. equals useful divided by the total, which is 165 joules, multiplied by 100. Okay, now let's rearrange the formula. Useful energy equals to us. You need to take this to the other side as a multiplication because it's a division here, and you need to take this to the other side as a division since it's a multiplication here. The way it's going to look is 15 multiplied by 165 because here it was divided. On the other side it's going to be multiplied, divided by 100 because here it was multiplied. On the other side it's going to be divide. You just need to do these numbers together. I just put all the numbers in the calculator, and the useful energy is 24.75 joules. Does this give me the final answer I'm looking for? No, because I don't want the useful energy. I'm trying to find out the energy transferred to the thermal store, which is I want to know how much is wasted. So in order for you to get the wasted, you know that the total energy is the useful plus the wasted. So all you need to do in order for you to find out how much energy was wasted, you can say that wasted equals total minus useful. Okay, and I hope you guys understand this because the total energy, look, at the beginning I had 165 joules. 24.75 of them were used into making the thing roll forward, so they were useful. And the rest of them all were transferred to the thermal store of the surrounding. I'm trying to find out the rest of them. So all I need to do is take the total that I had, which is 165, minus how much was used to move forward, and the rest is all that went into heat and whatever. So if we just subtract both of these together, 165 minus 24.75, we're gonna end up with 140.25 joules. Okay, and this is one way to answer the question. There is another way that's a bit smarter here. Let me add a page. Can I add a page right here? Nope, that's not what I'm trying to do. Okay, the other way that you can also use to answer the question, you go to the formula which says the efficiency equals useful divided by total multiplied by 100%. Okay, and what you can do is instead of you putting an efficiency of 15%, you can flip the question, and instead of putting 15 like we did up there, you can put an efficiency of 85%, and I'll explain to you right now why. Look, any percentage is supposed to add up to a full of 100%. If 15% were useful, then how much was wasted? You just gotta ask yourself the question. 100 minus 15, which means the wasted was 85%. Okay? Now, because I know the wasted energy is 85%, I can use the numbers to calculate how much energy was wasted. All I need to do is do 85 equals, which is the efficiency equals, but instead of the normal formula saying useful on top here, because I'm using in a percentage of wasted, I'm gonna have to scrap that and write wasted here. Divided by the total, which is 165 multiplied by 100%. You just need to understand either formula, but the principle itself is important. I really recommend that you understand doing it this way and why I use these numbers instead. To calculate it, we need to reshape it again. Becomes wasted, just to make it look more organized, equals 85. This was a division on this side. I'm going to take it on the other side as a multiply. This was a multiply. I'm going to take it to the other side as a divide. Okay. If you put these numbers in the calculator, 85 times 100 and 65, and divide them by 100, you will end up with the exact number that we got up there, which is 100.25 joules. Doesn't matter if you do it this way, if you do it the other way, they will give you the exact same answer. I like this question a lot. It's very, very, very nice. Okay. Draw a labeled Sankey diagram for the energy transfer. You can do the labeled Sankey diagram with percentages, or you can do it with the energy. It's up to you. Okay, all you need to do is draw it like this. Okay. Excuse my drawing. This is 15%, the useful, and I'm gonna make the wasted way bigger. Okay. Because it's 85%. I need space. All right. So this is a comparison. The total energy that we entered right here is 100%, aka 165 joules. And that's the total elastic energy. And then we can see from the diagram that some of it was useful, which was 15%. Okay. Or when we calculated it, it happened to be 24.75 joules. You can write either. Okay. And this turned into kinetic energy because it was useful. And remember, the entire thing is a toy and it has wheels and it's supposed to move. So turned into kinetic energy. And then right here we have the wasted that we label as heat, which was 85%, or some people want to do it with the other numbers, so 140.25 joules. Okay. All right, I think this is good. The video has reached 40 minutes. We can stop here and I'll make another video to continue explaining the rest of the paper. Feel free to ask me in the application, take a screenshot of any question that you don't understand, send me a message and I'll respond to you and re-explain it in a better way. Thank you very much for listening and good luck.